Hello? Yeah. Um, Hi again. My name is Bryan Maldonado from Oak Ridge National Lab. I'm here to present this paper in behalf of Nolan, who couldn't make it. So again, acknowledging my co-authors and the support from the Department of Energy on this development. Here, I'm going to present a digital tool to do an automated segmentation and analysis of concrete slab. Um, this is quite important in the US in order to evaluate the flatness and levelness of slabs before a new construction is raised. So the problem is that if you are pouring concrete, ideally you would like it to be flat to build the structure on top of it. If you have prefabricated components, as in this example, you can see that you can lift your prefabricated walls, but then the moment that you put the roof, then you're going to have a compound error because your original assumption that the slab was flat was not met. There is a standard that has to be a procedure that has to be done in order to determine this flatness. And two numbers are calculated. You can, this is the American standard, the ASTM E1155. And then this method tells you exactly what you need to do in order to evaluate the flatness of your slab. However, this is quite time consuming. And new state-of-the-art techniques use laser scannings, but again, you have a point cloud that you have to manually segment. So this solution is trying to overcome two things. One, the tediousness of the manual method, and second, the automatization of point cloud processing for slabs. Let's discuss the manual method first. So in this case, what you do is you have to mark some lines on the slab. This takes time from half an hour to 1 hour. And then you have to walk a profiler along those lines. So this machine is quite clunky. Basically, you have, it looks like you have an extra pair of feet and you have to walk the machine like this side to side. And the machine is like a profilometer and it's measuring the flatness and levelness along the lines that you previously marked. So as you can see, it could take quite a bit of time. And then you have to take the data back to the office, analyze the data, and then generate a report according to the standard. So these will take up to 3 days. And you know, you have to have basically your slab waiting for you. And then if in 3 days you come back and say, oops, it's not, the flatness is not according to what we need, then you have to rework it. Either add more concrete to the low spots or remove the concrete from the high spots. Now, from the state of the art, you do have laser scanning, which could be quite fast. We have actually a scanner that can scan an entire slab in less than a minute, depending on which type of scanner you have. The problem is that then you have to do the segmentation manually. And then you have to follow this standard on the point cloud in order to calculate the numbers. So it could be faster, but as you can see here, it's still like 2 days that it could take. So our method is trying to accelerate this process. So in this case, what we're proposing to do is scan the slab. So again, the timing of scanning depends on the equipment that you have, but then the rest is fully automated. So it performs automated segmentation. So this is an example of a slab that we scan, and then you can automatically extract only the slab, removing everything else. And then you run automatically the ASTM standard that generates a heat map with highs and low points. So this could take, if you have a fast scanner, this could be in less than a minute. So then it's faster. You do not need to have this tool walk this tool around the slab. But most importantly, this could enable real-time correction. So if you're able to do this fast enough, you're able to rework the concrete while the concrete is still malleable. So that is the best advantage for this method. So I'm gonna walk you through the workflow. This is, as I mentioned, an example that we scan. First, we have the dense point cloud of the slab with around 20 million points. Um, then we don't have to be super accurate to detect where the edge of the slab is. So we can do a voxel downsampling down to around 500,000 points. And then DB scan has been one of the best. Sorry, no. Then you do ransack, right? Ransack is a technique to identify kind of like the main plane of the point cloud. And obviously the main plane is going to be defined by the slab, which should be the most flat thing that you have in the scan. And once you do ransack and kind of like identify where this plane is, DB scan is a unsupervised machine learning method that will identify the most dense cluster that you have in your point cloud. So we have used it before and it works quite well. Then once you have the isolated slab, you can rotate it and make it align with the major axis. Then you can detect the edge. So do you edge optimization to determine where is the edge of the slab? Because you need this edge in order to go back to the original point cloud. Because remember that we did downsampling, so we're not working with all the points. So then you have to go back to recover all the points from your slab in the raw point cloud, such that you obtain a fully dense isolated slab, and then you can run the analysis on it. So the SATM standard basically tells you if you have your slab, you have to define this allowable measurement area, which is in this gray dotted line. And then you have to throw these sample measurement lines, which the program does automatically because it knows the size, the dimensions, the shape of the slab, so it can do it automatically. And then you identify these points. These are the points that you measure with this clunky profile machine. And then you compute your floor flatness and floor levelness numbers according to the ASTM standard. These current limitations, the first one, assuming a rectangular slab is not true anymore. This was true at the time when the paper was written. We have overcome these limitations, so we actually can have a combinations of rectangles or triangles. So this is not a limitation anymore. We can do more than just rectangular slabs. Single elevation, however, is a problem still. So if you have a slab that has some stairs, for example, we cannot do that. We need to have one common plane for everything to analyze. And yeah, this is the point cloud that we use. These are the results. So ransack is a randomized algorithm in order to identify this common plane. So because of this randomness, we ran the algorithm for 100 iterations. So you can see here the statistics of it. Ransack works in the segmentation side, so that is why you see this wide variety of numbers. Because if randomly here in the first number, you can randomly identify the plane and then you're done. But if you are not lucky, then you have to like look for it and it takes time. That is where the randomness comes from. But in general, now if you compare these two numbers, so on the right side, you have the automated floor flatness and floor levelness from this algorithm. The manual numbers were done following the ASTM standard on the point cloud, so manually drawing the lines, manually picking the points. So you can see that they are close. And again, this is an average measurement because these are results of is a statistical result because of the randomness of the ransack algorithm. But the numbers are quite close, and most importantly, you gain time by doing this automatically. So in our ongoing efforts, we are working on minimizing this variability. I believe I heard Nolan saying that he has a way to do this more with less variability, so more predictably, to have a really good time number for this. Point number 2 is already done. We can do it with the slabs of different shapes. This is something that we'll publish probably soon enough. One of the things that we have struggled is to collect data. So there is not a lot of contractors that are allowing us to scan slabs because probably they don't want to know how bad the slab is. I don't know. But we're trying to do our own concrete pouring, at least a small sample, in order to test this. But we really have struggled. So if you all know of anybody who wants to collect some point cloud of slabs, please let us know because we really need to collect some data. So just to conclude, I have presented this tool that can automatically scan a slab, identify where the slab is, and then compute the floor flatness and floor levelness numbers according to these ASTM E1155 standard. It might be different. Europe or Asia might have different standards, but we are working under this American standard for now. And with that, thank you. You can email Nolan if you want to contact him. Thank you.